Let's start. First off, agenda for this week. My plan is to finish chapter 7. Really hoping that we can do this week. And even better if we can start chapter 8, which is the isolated converter, the push-pull, flyback, and forward converter, those three topologies. And then we will have quiz number 6, due this Friday, 11:59. My advice for you is to wait, not to take it yet until we're done with chapter 7. Okay. The more you know about chapter 7, including the more you hear about the concepts on chapter 7, including those will be covered in lecture on Thursday. The better it is, right? So the quiz is going to be on DC to DC converters, and that's why it's important for you to review those pages that I have right there, pages 291 to 349 before you take the quiz. Even better if you wait until we're done with our lecture on Thursday. Okay, it's up to you though. It's up to you. If you feel like you're ready, you can go ahead and take it up. I'm not sure if I have it available yet. If not, I can do that after class today. So you can go ahead and take it. Okay, and then homework number 6, that's going to be this Friday as well by 5 p.m. That's another thing. Before you take the quiz, it'll be useful if you, or helpful, it'll be helpful if you do the homework first, because that homework also is on DC to DC converters. Okay, so the more you practice, the better it is for you to prepare yourself for the quiz. And then lab number 7. Hang on a second. Lab number 7 this week. We're going to start the isolated topology, even though we have not covered the topic yet in the lecture portion, but I'll go over push-pull in the beginning of the lab, starting today, today's section. Yeah, if you could review also before we go to the lab today, and then also Thursday, pages 380 to 398, that'd be good as well. And then the report is due Friday, 11:59. So you have 3 things that are due this week and that are due this Friday. You got a quiz, and then homework, and then lab report, all on Friday. Any question on this? Okay. If not, let's continue our discussion on buck. We're almost done with buck converter, right? Just one more thing that I want to go over slowly, and then after that, I'm going to go faster. This next one is not as simple as determining voltage rating or current rating of the components. This is more involved in terms of calculation. It could be actually it could involve long equations depending on the waveforms that's involved in the calculation. So this relates to determining or sizing capacitors. Okay, so I'm going to go through this slowly, right? Maybe for a couple times, output capacitor and then input capacitor, and then after that, when we move to the other topologies, I'm going to go faster when we cover capacitors. Okay. Okay, here we go. So capacitor, when you size capacitor, you need 3 things. The first one is the capacitance, right? That a capacitor should provide enough capacitance to maintain a given peak-to-peak capacitor voltage. That fluctuation in the capacitor, right? So if this capacitor is connected to the output, right, and you want to make sure that the output fluctuates around a certain average value, right, then that fluctuations will be maintained in addition by the controller, also by the capacitor. Okay, so it requires a critical capacitance to be able to maintain that certain peak-to-peak output voltage ripple, or not just output, but voltage ripple. In general, voltage ripple across the cap. In order to do this, you need to know the ideal capacitor current waveform. So this is very important. This is the very first step. Okay, knowing the ideal current that flows into the capacitor. We'll go over that next. Then apply the charge equation Q equals to C delta V. That's the second step. And after this, you can just solve for C. Look at this equation, Q is equal to C delta V. You're looking for C, capacitance, right? So two steps, okay? Knowing the ideal capacitor current waveform, number one. And number two is to apply Q is equal to C delta V, and then solve for C, okay? That's the first thing you need to know for sizing a capacitor. Secondly, of course, you need to know the voltage rating of that cap, and usually this is not bad at all to determine, right? If it's if the capacitor is connected on the output, obviously it's going to be rated around the output voltage, right? If the output is 5 volt, then the rating of that, the voltage rating of the cap, right, should be larger than 5 volt, right? So that one's not bad. This one could also be bad right here. And then the third one, so typically, normally every EE student will know that if they need to buy a capacitor, they need to know the capacitance value as well as voltage rating, right? I think every EE will know this. The third one that not many EE students know, and in addition to that, this actually relates to specifically this class, right? Anything to do with power applications. You also need to know that the capacitor must be able to handle a certain AC RMS current, right? Because there's going to be current flowing through this capacitor, and you want to make sure that this capacitor can handle the RMS value of this current, right? Why? Well, because this current translates into heat, right? And the reason being there is ESR in this capacitor, right? And we know what ESR is. ESR stands for equivalent series resistance. So every real world capacitor will have ESR, right? So imagine if you have ESR in series with the cap, right? And then you have current, AC current flowing through that ESR, then of course that would that ESR would dissipate power, right? Exactly equal to I cap RMS square times ESR, right? So if you do know ESR of the cap, then by also knowing the RMS current, you will be able to calculate loss from the cap, right? And you want to make sure that the cap can also handle this RMS current, okay? So three things, okay? Capacitance, voltage rating, and RMS current rating of that cap. Okay. Here's a picture of the output stage of a buck converter. Remember, a buck converter has inductor on the output stage, right? And then we want to put capacitor to filter out the output. And then there's the load right there, the resistor. And then there's the ESR right there, right? So if the current that flows through this capacitor, right, flows through that ESR as well, then of course you're gonna have some heat dissipated into that ESR. And here's the equation, right? That current by KCL, right here, oops, by KCL, current into that node, which is IL, right? That's current through the inductor, IL, must equal to I out or IR plus IC, capacitor current, right? That's the equation for KCL. And we also know that IL by itself, since it looks like this, we already know this, right? That IL looks like a triangular waveform. Then we know that the triangular waveform or inductor current waveform consists of two components, the AC component and the DC component. So IL itself has AC component and has DC component, right? So right there, IL AC, IL DC, average is also equal to DC, right? And now we know that the DC the DC portion of IL will not or cannot, right? Forget about ESR for now, right? This is an ideal equation, of course. The DC component of IL will not flow through capacitor, right? Because capacitor is blind to DC, right? So therefore, because the DC component cannot flow through the cap, the DC component of IL must only flow through the resistor right here, right? But AC is a different thing, right? To an AC, capacitor looks like a reactance, right? So therefore, the AC will flow through the cap, will be sucked into the capacitor. So now we have, ideally, the inductor current splits, right, into the load and the capacitor, right? The component of the inductor current that flows through the cap is the AC component, which is the ripple portion of this, the ripple portion of this current, whereas the component of the DC component of the inductor current will flow through the load. Any question on that one? So here's a picture of IL right there. And IL has the, if you take away the offset is our DC component right there. That's our offset, right, from that inductor current. Then you are left with the AC component of the inductor current. So here's the AC component right there, right? You can see we have a triangular waveform and it's centered around 0, and this area is equal to this area, right? Why? How do I know that this area is equal to that area? What is the answer to that?
Second balance.
Yeah, what concept that we learn that proves that those areas must be equal?
M-second balance.
Very good, very good. M-second balance. So we know that based on M-second balance, the average current through the cap must be equal to 0. In order for that to happen, we know that this area, positive area, must equal to the negative area. Very good. Okay, so remember I said earlier about knowing the ideal current waveform through the cap? That's what I meant. This is what I mean right here, right? By drawing the corresponding waveforms that is connected to the capacitor, then you would know the ideal waveform, the ideal current waveform that flows through the cap, right? Right now we're talking about output cap of a buck, right? Turns out to be that the output capacitor of a buck relates to, in terms of the waveform, relates to the shape of the inductor current waveform, right? Because the current comes from the inductor. So you can see now the reason why the output capacitor waveform of a buck shapes like this, right? Because it comes from inductor. Now, of course, it's not always like this. It depends on the topology, right? It depends on how the capacitor is connected in the circuit, okay? So this is only true, right, for the output of a buck converter, for the capacitor waveform, capacitor current waveform of the output stage of a buck, right? This shape right here. Any questions? Okay. Okay, knowing that, now that we know the ideal current waveform that flows through the cap, I redraw that here, right? So I redraw that current right there. That's the very first step, right? In order to calculate capacitance. Remember I said there are 3 steps, right? Knowing the ideal current, the ideal waveform of the current through the cap. That's number 1. Number 2, apply Q is equal to C delta V. And number 3, solve for C from that equation. So I'm done with the first step. This is the first step right there. Very important step. Any question on that one before I move on to the second step? Okay.
Wait, can you explain again? Sorry.
I couldn't hear you. Can you say it again?
Can you repeat how the first step was? I didn't hear you.
I couldn't hear you as well. What did you say? How do?
Can you? I don't know what's wrong with my mic. Can you explain step 1, the number 1 you put, please?
Oh yeah. Now I can hear you. I don't know what happened before. but I can hear you now, Josh.
Sorry, I don't know what happened either.
All right. So the very first step is to know the shape of the current waveform through the cap. Okay. What is the shape of the current waveform through the capacitor? And that would be determined by where that cap is located, right? In a buck converter, let me go back. In a buck converter, the output capacitor is connected that way, right? And let me erase this. In a buck converter, the output capacitor is connected this way. You can see it's connected from the inductor and then across the load, right? And by knowing this, so this is the first thing you need to know, right? How the capacitor is connected in the circuit. By knowing this, then I would know that current through the cap, the shape of the waveform of the current through the cap must be derived from the inductor current, right? Because the DC component will not flow through the cap, it will go through the load. That's the DC component of the inductor current. The AC component of the inductor current must flow through the cap, right? Do we know the shape of the inductor current? Yes, we do, right? That's going to be just triangle waveform, just like that, right? And then all we need to do now is to determine what is the AC component, or how does it look? How does the AC component look from this inductor current? Right, well, how do we know that? By taking away the offset. Right? The offset means the average value, right? So the average value is the midpoint, right, between the peaks. So the dashed line right there is the offset. So if I take away the offset, right, see this is the offset right there, the average value which flows through the load, then I'm left with the AC component. So this inductor current waveform will be shifted down, right, if I take away the offset. And it will now look like this, right? And this is the current that will flow through the capacitor. That's step number one.
Thank you.
So, okay, hopefully that's clear.
Yeah.
Okay. Important, very important for you to know the shape of the current waveform that goes through the cap. Very important. Otherwise, the next step will be wrong. Right? So the first step right there is very important. All right, and when it comes to final exam, expect to see one problem like this, where you have to size capacitor. Okay, so important for you to pay attention and know the different steps in sizing capacitance, in finding critical capacitance. Any other questions?
Can I ask a clarifying question?
I'm sorry?
Can you hear me better?
Yes.
So is the AC component of the current going through the inductor basically the current going through the capacitor? Is that a good way of thinking of it?
Yes, for this example, yes. Yes, strictly for this example. Again, if I go back to here, right? This inductor current has AC component and DC component, and we know for sure the DC component will not flow right through the cap. It's going to be blocked. So the only current that will be attracted to the cap would be the AC component. Okay.
Thank you.
All right. Yeah. So yes, the answer is yes. For this example, the AC component of the inductor current will flow through the cap. Only true for this example, though. Right? Don't generalize this, because if you go to the next example, I will show you the next example on the input. It's different. It's a different story, but the concept is the same, though. Right? Okay. So look for the AC component. I think that's the general idea behind current through the cap. Look for the AC component of where that current comes from. But in this case, the current comes from inductor. So look for or determine the AC component of the inductor current. Any other questions? I just want to make sure that everybody's clear on this. I know I'm going slow. I'll do that on purpose because this is very important. No? Okay. Now that we're done with step number one, step number two is to apply, what did I say? Q is equal to C delta V, charge equation, right there, charge equation. That the amount of charge should be proportional to the amount of capacitance, excuse me, and also the change in the voltage across the cap, right there, delta V, right? So here's the amount of charge when the capacitor is charging. So basically, this is the amount of charge that is being stored, and here's the amount of charge that is being released, right, by the cap. That's why it's plus and minus. Plus Q means storing the charge, minus Q means releasing the energy, right? And we already established earlier that these areas must be equal, right? And so what's nice about a buck converter on the output side is that the shape, watch, the shape of the positive Q, look at the shape, is triangle, right? Is exactly mirror image of the shape of the minus Q. Agree? Because of that, right? Since we have the same shape, therefore, when you apply this equation, it doesn't matter if you choose the plus Q or minus Q. Well, it doesn't matter for any case anyways, but specifically in this case, right, it doesn't really matter because either way, you're gonna have to find the Q from triangle, right? Either plus Q or minus Q. If you wanna do the minus Q is also a triangle. If you wanna do the plus Q, it is also a triangle, right? So it doesn't really matter for a buck, right? In other cases, it may not be the case. It may not be as simple as this, right? So for a buck output capacitor, easy, right? Triangle, exactly the same, right? See Q right here. In order to find the amount of charge, you need to find the area, right, of either plus Q or minus Q. That's why I said earlier, it doesn't really matter which one you pick, right? In other cases, choosing minus Q might be simpler than using the plus Q because of the area that is contained within minus Q. You'll see later on, okay? But in this case, they're the same. And so when you apply Q is equal to C delta V, remember that Q involves finding the area, right? Area of the current waveform, either on the positive side or negative side, right? Because the area of the Q here, the area of the current, sorry, this is current, not Q, right? This is current, and you know from calculus or physics, I should say, that the area under current waveform is the amount of charge, right? Good. So that's what you put on the left side, the area of triangle in this case, either plus Q or minus Q. Pick one, and then on the right-hand side of the equation, we have C times delta V. Just leave it like that for now. See, just leave it as is for now. Now go ahead and look at the next one right here. You can see that I'm finding the area of the triangle, right? Because it is a triangle. How do you know? How do you calculate the area of triangle? 1/2 times the base times the height, right? What is the base? Well, the base from here to here is the entire period, T, right? So therefore, for one triangle, the base from here to here must be T divided by 2. Yes, because they're the same areas, right? So that's what I put right there, T divided by 2. What about the height? The height of that triangle, one triangle is going to be from here to here, right? And we know that this is coming from inductor current, right? And we know that for inductor current, if I go back up right here, right, from here, from the max point to the mean point, that's what we call delta IL, right? So therefore, if you take away the offset, now the waveform is centered around 0. And now we know that the height of this triangle, one triangle, must be equal to delta IL as well, divided by 2, right? And that's what I put right here, delta IL divided by 2. And don't forget the 1/2, right? Because that comes with the equation to find area of triangle. Okay, so the whole thing equals C delta V. Any question on this? All right. So now that we have this equation, I'm just going to simplify. On the left-hand side, I get delta IL over 8F equals to C naught delta V naught. And now I have that C naught right there. That's what I'm looking for, capacitance, right? And so I'm going to solve for C naught right there. Okay, good. Now, we have the equation for delta IL from last week. So I'm gonna substitute that here, right there. That's our delta IL, this whole thing.
Can you
Yeah,
just clarify how you got delta IL, like why you chose delta IL for the area of the triangle?
I did not choose. I got it from the waveform, right? So if you look at the waveform right here, right? Let me go back. I need to find the area of this triangle, right?
Yeah.
And what is the height of this triangle?
Height is your delta IL over 2. Got it.
That's correct. Yes.
Okay. Thank you.
I don't know if you can choose anything else, but I'm just going to choose the one I know, right? And so I know that's the whole thing from here to here is delta IL, right? That's delta IL. So therefore, halfway is delta IL over 2. You might be able to express express the same thing with different parameters, but I'm just going to use delta IL for now, because that to me is something that I know right away from the waveform. Does that make sense? Yes. Who asked? Is it Josh?
Yeah, it makes sense.
Okay.
Thank you.
You're welcome. All right, so then again, I'm solving for C naught right there. That's what I'm interested in finding. It's equal to delta IL over delta V out plus, or not plus, times 8F, right? And I plug in the equation for delta IL from last week for a buck converter right here, right? So now it's a longer equation. You can see now it's equal to V out 1 minus D times T over L. Can you tell me whether or not this equation of delta IL comes from delta IL off or delta IL on? Which one?
Off.
Off, very good. How do we know that? Because of the 1 minus D times T, right? So we know for sure that's T off, right? Remember that delta IL has 2 equations, one for T on, the other one for T off. Right? Why do I pick T off? Why do I pick T off? Well, because T off is a simpler equation than T on. If you go back to last week's lecture, the equation for delta IL for T on involves both V in and V out. Here, for T off, is only involving V out. So it's a simpler equation. When you could use delta IL for T on too, it'll give you the same result. Okay. Okay. Erase that. So then over here, I'm just rewriting the equation, simplifying the equation. As you can see, at the end, I have the final equation for output capacitance of a buck converter. Okay. I'm gonna discuss several things here, so please pay attention. This is practical issues, okay? This is not theoretical. This is more practical issues. All right, if you look at this equation right here, very important equation for sizing the output capacitor of a buck, very important, right? You're gonna need this when you design a buck converter or a boost converter. Boost converter is gonna be a different equation, of course, but for a buck, that's the equation. Now, what I would like to discuss is the practical implication of this equation, right? Okay, let me start with a question to you. Out of these parameters, you can see that output capacitance is a function of duty cycle, function of V out, function of L, function of F, right? Out of these parameters, right, that determines the output capacitance right here, which one do you think is which ones are in practice pretty much given to us? Anybody?
Frequency, output voltage.
You said frequency and output voltage, okay? Very good. Who else? Any other opinions? Remember that in practice, you want to minimize, right? You want to minimize output capacitance. Why do you want to minimize output capacitance? Many reasons, but the two main things would be cost right? And also space or volume, right? So so one person, I don't remember who said who said that earlier. Output voltage and frequency. Anybody else has any different opinion?
Maybe inductor size.
Inductor size. Okay, very good. Okay, very good. Okay, those are good answers. But my opinion is this, right? So based on my experience, the one thing that's typically given to us, number one is V out, right there, right? And which also means you are given delta V out. Typically, you are given delta V out, meaning a customer will the customer will specify this for you, right? I want a DC to DC converter whose output is 5 volts, and fluctuation on the output should be within, I don't know, 5%, 3%, what have you. So these are typically given, right? So you don't have any freedom in terms of choosing your cap based on the out, right? But these parameters basically fixed or given to us. What else? I would say duty cycle, right? Right there, duty cycle. Why? Because again, typically before we design a converter, not only that V out is given, input is also given, right? Input voltage is also given. So you must know what input voltage is, and that's typically given by the customers as well. And they would say, okay, the input voltage would have a range between 10 to 20, right? So because that is given by the customer, then therefore this is basically a constant. You don't have any freedom for duty cycle in order to minimize this, right? What about F? F could be 50-50, depending on, well, sometimes, you know, the customers will say, okay, the switching frequency must be higher than certain value. Well, let's say it must be higher than 500 kilohertz. In that sense, you know, yeah, it's fixed, but then you still have the flexibility of choosing whatever frequency above 500 kilohertz, right? So you have freedom to, you have the flexibility of minimizing C from F from that sense, right? But sometimes, you know, unfortunately, it is a fixed value. You know, it is not something that you can choose. For example, the customers specifically want you to use a certain controller, right? Let's say, I don't know, LT, whatever it is, or Maxim, or MPS, or TI, whatever it is, right? Controller. And you look at that controller, and from the data sheet, it may say, oh, for this controller, the switching frequency is fixed at 300 kilohertz, right? So from that kind of case, then you know that F will be fixed because you're stuck with this one controller that turns out to be giving us only a fixed frequency, right? So that's the frequency. So yes, 50-50 in my opinion, right? May or may not. The very last one is L. This is something that I believe, right, that you have the freedom of choosing, right? Very rare that the customer will specify, okay, design a DC to DC converter that has L of such and such microhenries. I never seen, in my past experience, I never seen, you know, a customer specifying L. We are the designer of the converter, so we specify L, right? What is L? Well, critical inductance, right? Remember we talked about it last week? So out of these parameters, L will be the one that you have flexibility of, right? In terms of minimizing C, right? And you can see from this equation, let me erase this. You can see from this equation that C is inversely proportional to L. Now you know another advantage of increasing L, right? We talked about several advantages last week. There's another one for output capacitance. As you increase L, you decrease C. That's a trade-off though, right? because you don't really want to keep increasing L, because otherwise your DC to DC converter is going to be big because of the size of L, right? So there's going to be some, sweet spot for balancing the two. Okay, does that make sense? So from practical point of view, right, out of these parameters, you have the freedom of choosing L. You have the flexibility of choosing L to minimize C. Hopefully you have others as well to play with. Right? Hopefully the frequency is not fixed, right? So that you can again play this game between balancing L and F to minimize C. Right? But most likely the output voltage and duty cycle will be fixed. So you can't do anything with those two. Any question on this? No? All right. So that, if you look at the equation, it is very simple equation, just plug in chart type of equation, but I want you to understand, okay, the practical implication of this equation, the one that I just discussed with you. Any question on that one, on the practical implication of this equation? All right. If not, so you can see that the way I wrote this equation right there is the ratio. See that? Delta V out over V out. Well, that's called a percent peak-to-peak ripple, right? Fluctuation on the output voltage, the amount of fluctuation divided by the average output voltage itself. So typically this is given in percent, right? So for example, customer will say, okay, I want peak-to-peak ripple on the output voltage to be 5%. So that's 5% is right there, delta V out over V out. So you put 5% for that one, okay? Any questions? So you can see that's inversely proportional as well, right? The lower the percent, meaning the smaller the fluctuations, the bigger the capacitance required, which makes sense, right? Imagine if peak-to-peak ripple is 0, that means it would require infinite capacitance. So this equation makes sense to me. All right. Okay. Now that's just.
I had a question.
Go ahead. Go ahead.
Is it usually more preferable to have a smaller inductor, larger capacitor? Or does it depend?
That's something that you have to determine based on whatever it is conditions that you're designing this for, right? As I said earlier, this is why we need to know the practical implication of this. So there's no one answer to that question. For some applications, you do want smaller inductor, and that way you can balance the size with the capacitance that you pick, because you can see from that equation, the smaller the inductor, the bigger the cap, right? But then you play around with the sizing of this C and L. Some others, I don't know, you are not constrained in terms of volume or space of this circuit. In that case, go ahead and put in, as big as inductor, right? But keep in mind there's budget behind this equation as well, right? So unfortunately, I will not be able to answer that question at all. There's no one answer for that question.
Okay, thank you.
Okay. All right, so that's capacitance, finding capacitance. The next one is finding RMS value of the current through the cap, right? And if you already know the waveform through the cap, current waveform through the cap, then finding RMS will be just applying RMS equation to that waveform. So we know for the output capacitor of a buck converter, it looks like this, right? Let me erase this again. That's our current right there for the cap. The current through output capacitor of a buck. It looks exactly like this, ideally, of course, right? So then when we are asked to find the RMS of this, then it's just a matter of finding the RMS of a triangular waveform for this case, which is not bad, right? For a buck output of a buck converter, output capacitor of buck converter, right? Finding the RMS of the triangular waveform is not bad, right? Because we know that the RMS value is equal to peak divided by √3, right? So that's what I have right here. And we know that the peak value is equal to delta IL over 2. Right there. Delta IL over 2 divided by root 3. See that? Okay. So for the output capacitor of a buck converter, finding RMS current through that output cap is easy. It's just delta IL over 2 divided by root 3 because it's a triangular waveform. And now, once you have this equation, it's just a matter of replacing delta IL, just like before with the equation that we learned last week, either with T on or T off, right? Here's with T off right there. If you change delta IL with the equation for T off, or you can change it with T on, delta IL on. So you have two equations to calculate the RMS current through the output capacitor of a buck converter. It doesn't matter which one, right? It should give you the same answer. All right. Any question on that? That one's not that bad. Once you know the equation for the RMS equation for the current through the cap, then you can calculate power loss, right, of that capacitor. If you know ESR, if you know the ESR of that cap, then power loss of the capacitor will be the RMS square of the current times ESR. Right? So just this equation, any one of these, square it times ESR gives you loss for the output capacitor of a buck converter. Okay, any question on this? Okay. Voltage rating, as I mentioned earlier, is very straightforward because this is on the output voltage, right? It's on the output stage. The capacitor is connected straight to the output, right? So therefore, the voltage rating of the cap should be larger than the output voltage, or precisely should be larger than V out average plus the peak of the fluctuations. Remember, delta V out is the fluctuations of the output voltage, right? And the fluctuation is around the average value. Let's say this is the average value of the output voltage, let's just say, right? Then fluctuation around it will be around that average value, right? So therefore, the cap, the voltage rating of that cap must be equal to the average value plus delta V out divided by 2. Any question on this equation right there? No? All right. So we're done, right? We're done with sizing the output capacitor of a buck. Remember 3 things, right? Capacitance, critical capacitance, RMS of the current through the cap, and voltage rating. Okay. I'm going to go through the second example, input capacitor of a buck converter, right? Of course, ideally, if the voltage source is an ideal voltage source, you don't need input capacitor, but we know very well that in real world, we will not have any ideal voltage source. So you will have to put input capacitance. So how do you size input capacitance of a buck or input capacitor? How do you size them? Well, again, you're gonna need 3 values. Number 1 is voltage rating. That one is the most straightforward one, right? Because this is connected across input. Therefore, the voltage rating of that cap at the input would be V in plus the fluctuation that you allow for input voltage, delta V in over 2, just like the previous one we did for output voltage. Okay. Any question on this one? And typically delta V in is given, just like delta V out, how much fluctuation you want on the input voltage in terms of %. Okay. The more challenging one to calculate is critical input capacitance. Now I already see a mistake here, so please change this in your textbook. This is supposed to be upward, not downward. So please change the arrow right there to be upward. Sorry about that. Okay, that's at the input of a buck, right? I'm gonna draw a buck converter. That's a buck converter right here. The power stage, right there. So you can see that the input is connected to the source, right? In other words, that capacitor acts like a source, right? So that capacitor, if I want to group that together, it's going to be across the source. Now you have the buck, right? This is the buck converter right here. Whereas the output consists of the cap again and the resistor, right? So if I use different color here, here's the output stage, and here's the input stage. See that? So the output cap acts like a load. The input cap acts like a source to the buck. Okay? Anything in between the two, that's a buck power stage right there. Right? This is buck. Any question on that? So that's why this arrow has to be pointing up, because it's sourcing, not absorbing, not dissipating, not taking power, but it's supposed to help in terms of power. Make sense? Okay. So please change the arrow again one more time to upward for the capacitor, right? Indicating that's how we reference the current through the cap is upward. Right? If that's the case, then if you agree with that, then if you take a KCL at that node, what do you get? You get I switch, right? Current through the switch must equal to I capacitor plus I in, right? And just like before, remember, we are trying to find a capacitor current, right? We need to know the shape of the current through that cap, right? So therefore, we need to know how that cap is being placed in the circuit, and which component it is connected to, right? So that we know the shape of the current through that cap, right? So in this case, we know that this capacitor current must be derived, right? Because those two currents right there add up into switch current right here. So therefore, I know that the capacitor current, the shape of the capacitor current waveform must be derived from the shape of the switch current, I switch of T. Right there, this is the equation. So I know that the shape of the capacitor current must be derived from the shape of the switch current. Is that clear, first of all? Any question on that one? All right, so then now it's just a matter of knowing the shape of the switch current. If I know the shape of the switch current, then I should be able to determine the shape of the current through that cap right there. Do you know how the current waveform looks? Of course we do, right? How does it look? Anybody? How does this current waveform look through the switch? Ideally. Come on, just one of you answer.
I am.
Like some trapezoid.
Yes. With the upslope or downslope?
Upslope.
Upslope. Why?
It's just half of the inductor current, or like the upslope part, and then the diode is just the downslope part, because the diode is on when it's conducting. I mean, when the switch is off.
Very good, very good. It's not half though, okay? It depends on the duty cycle, right? It could be half, it could be less, it could be more. Yeah, depending on the duty cycle. But very good, very good. So yes, we know that the shape of the switch current is a trapezoidal current waveform, right? With the upslope. Why? Because we know that every time the switch is on, we are charging the inductor. That's what we learned last week. That's why I went slowly, right, last week, so that you understand that anytime that switch is on, we are charging the inductor. So we know that the current, the shape of the current through that switch must be right here, right? Trapezoidal current with the upslope right there, right? Now, why is it important for us to know? Because then we would then be able to determine the shape of the current through that cap, right? How? Well, because if I go back to here, because I know from this circuit, if I clean this up a little bit, I should not, okay, ignore this again, sorry about that. up right there. And we know from this picture that capacitor can only supply the DC current into the switch, nothing else, right? And so if the capacitor can only supply the AC component, therefore the voltage source will only supply the what did I say? Sorry. If the capacitor can only supply the AC component of the switch current, therefore the voltage source will only be supplying the DC component, right? So just like before, this is going to be I of AC of the switch of I switch. Right? So I switch AC basically, right? And then this one will be I switch off DC. Right. So that's what I try to draw here. Right. Here's we have switch current up here. That's the switch current. The average value or the offset will give us the current through, or the current from, I should say, the current from the voltage source right here. Right. This is from the source. Right. Oops. Misspell source. And so the AC component of that switch current, which is right here, right, that's the AC component of the switch current, must be flowing into our input capacitor, IC in, right there. Any questions? So you take away the offset of the original switch current, you take away the offset, then of course this waveform will be shifted down from here to here. Yes. Now you can see that this waveform is not as easy as the previous capacitor current waveform, right? In the previous case, we have a triangular waveform. In this case, we don't. Right. Notice that, let me erase this again. Notice that that the amount of current that is being shifted down right here, I see here, right there. We should know that, right? How much is this waveform being shifted down? Well, that's exactly I switch average, right? Exactly the average current through the switch. So whatever that is, that's how much this waveform will be shifted down. So that's why I know that from this point to this point must be I switch average. Good? All right. All right, knowing that, then I redraw that current because that's our capacitor current. Any question on this? Now we know the shape of the current through the input capacitor. The shape is like this. This is ideal case, of course, where we have no losses in the system. No? Okay, so then that's the first step, right? Being able to draw the current waveform through the cap. What's the next step? We apply Q is equal to C delta V right there. Q is equal to C delta V. Right? Remember, Q is the area under the current waveform, right? It's either plus Q or minus Q. Right? And then we have C in and delta V in. Just like before we have C out and delta V out. Now is C in times delta V in. Now, if I have to choose in terms of finding the Q, right? Which one should I choose? I would choose the easier equation, right? Between the two, we have the area of the trapezoid or the area of a rectangle. I'm going to use the area of rectangle, right? Because that would be easier to find than the area of trapezoid. So that's what I'm going to do. That's what I actually did right here, right? Area of the minus Q. So I pick minus Q. Remember before with the buck converter, it doesn't really matter if you whether you pick the plus Q or minus Q. Why it doesn't matter earlier? Well, because the areas for both is triangle waveform, right? Or triangles, I should say. Here we have different shapes between plus Q and minus Q. So I pick the easier shape to find the area, right? So I know that the area of a rectangle is just the width times the height, right? And the height is the average of the switch current. And the width, be careful, since I picked minus Q, that means this minus Q from the time from here to here belongs to T off, right? If I go back up right there, you see this? this original waveform from the switch, right? This is T on from here to here, and here is T off, right? This is when the switch is on, this is when the switch is off. So therefore, the width of this rectangle is T off. No. There it is right there, okay? The height, the width. Any question on this? Okay, so then the next thing is to solve for C in. Don't do that, please. Okay, here. So C in right there is equal to I switch average, then T off, right? That's our T off, 1 minus D times T divided by delta V in, right? And we want to do worst case, right? Worst case value. So worst case value happens when the average of that switch current is at max value. That's why I put max right here, right? Because this current right there, this switch current, going back, come on, right here. Can you hear me still? My internet is unstable, it says. Can you still hear me?
Yeah, we can hear you.
Yeah.
Okay, so I was gonna say that this switch current, it may go up and down, right? Depending on the load current. So it may be going down this way, right? When the load is low, or going up when the load is high, right? So of course we want to size the capacitance based on the worst case scenario, which would be at max load, right there. Okay. So that's why I put I switch average max. So this corresponds to, let me go back here. This corresponds to I out max. Okay. Right here, I have it right here. See that right there. Right, and how come I have I switch max equal to D times I out max? Where that come from? Anybody remember? For a buck converter, let me go back here. For a buck converter, okay, buck converter. Right, here's our I out. Here's our IL, right? Here's our IC. We know that IL average is equal to IC average plus I out average, right? IC average is equal to 0. So therefore, for a buck converter, IL average must equal to I out average. Agree? So then for a max, of course, IL max is equal to I out max. Yes? And then in that equation, I put I switch max right there, right? Well, before I go there, I know that I switch average must equal to blank IL average. Can you fill out that blank? What is that blank equal to? Anybody?
D.
D, very good. Remember, I asked you to memorize this, right? The average current to the switch is D times IL. The average current to the diode is 1 minus D times IL. Right? Remember that. Okay. Now, IL average for a buck, I just derived that to you right here, is equal to I out. Right? That's equal to I out. So therefore, if you look for I switch max, that's going to be D times IL max, right? Which is also equal to D times I out max. Any question on this? No? All right. So that's why I put D, I switch max equals to D times I out max. Now you know why. Good. And then the rest is just simplifying the equation, and you get the equation right there for input capacitance. Any question on this? So that's how you size input capacitance or critical capacitance of the input capacitor for a buck. One more. We did the voltage rating. Now we get the critical capacitance. The last one will be RMS current through this cap. in the previous example where you have triangular waveform, that's easy, right? That's just peak divided by √3. This one is not going to be that easy, right? I mean, take a look at this current waveform. How do you calculate RMS for this, right? It's not that easy. So what I did is this. I believe that's what I did. Okay, let me erase this. Right, I need to know the RMS value of the AC component of the switch current, right? Come on, hurry up, hurry up. There you go. Okay, good. See, I need to find the RMS of this. I need to find the RMS of this, right? Which is the RMS of the AC component only, right? That's the AC component of the switch current. I do have the total current right there, right? That's I switch total RMS. And I do have the offset or the DC right there, the DC component of the switch current. So one way to calculate the RMS of the AC current only is by using the geometric sum. Remember the geometric sum? That the total RMS of the switch current must equal to the square root of I switch AC only square plus I DC only square, right? And so if I solve for if I solve for the AC component only, then the equation becomes I switch AC only RMS must equal to square root of I total RMS square minus I DC square. Yes? So that's what I do, right? Because I know what I switch average is, right? From the given parameters. That's just average of input voltage, average of input current, right? And then this one, you see this shape right there? Do you know how to calculate the RMS of this? The answer is yes. You have to go back to chapter 2. Remember, one of the entries in the table has this shape right there. So go back to that one, and the shape of this one is just flat. So you know the RMS of a flat. That's easy. Right, so therefore, that's the method I use. I don't know, maybe you can find a different method using integral, which I don't want to use. I just use that method right here. So this equation, I got it from chapter 2, from table, one of the entries in the table. And then this one is just I switch average, right? We just talked about it. That I switch average is equal to IL times D, right? And then as you can see, you look at the algebra here, ugly, right? And then at the end, I skip, of course, I skip some of the equations I derived. But then at the end, you get the RMS value of this current right there. Long equation, unlike the one that we have before for the output cap, right? Any question on this? Okay, no questions? All right, so the next time we see capacitor for a boost and buck boost, I'm gonna go fast, okay? Any questions before I move on to boost converter? All right, if not, let's move on to boost converter. I'll let you read through these capacitor selections. You know, those are additional notes. And please go through these examples. These are all plug-in chart problems. And then I simulated it, and you can see the buck converter that I simulated right there, right? And then you have this output voltage. I designed it for 2.5. You went through this exercise in the lab. That's why I'm skipping through this, because again, we did this exercise in the lab. And you can see the inductor current, as expected, is triangular waveform. The switch current, as we expected, is a trapezoidal current, and as well as the diode current, right? And you can see that inductor current is more DC than the other two. Why is that? Because it's continuous, right? There's no gap, right? There's no segments that goes to 0 and stays at 0. So this is more DC than the other two, right? You can see this switch current and diode current is ugly, right? It's nowhere close to DC, right? Because it's discontinuous. See that discontinuous part of this current, the 0 portion there. Same thing here for the diode, right? And because of that, a buck converter is bad good in terms of input-output characteristics, input-output current characteristics. because the input stage of the buck converter is connected to a switch. So therefore, the input stage has to handle this kind of current, which implies a bigger filtering requirement. Whereas the output stage of a buck is inductor, right? So it has to deal with a better current. This is a much better current than this, right? So therefore, the filtering requirement for output converter of a buck is less than that of the input of a buck, right? Bad, good. That's a buck converter. Any question on those? Ah, there it is, input-output characteristics. Buck is bad and good, okay? All right. Boost converter, all right. Let me start from here. So let's start with a buck, right? I want you to memorize a buck converter, right? Start from the first letter of my name, right? T. And we know that for a buck converter, the input is a switch. The output is inductor. And if you have switch and inductor, the last component must be the diode. That must be in the middle, right? So that's a buck converter. A boost is the opposite of a buck, right? A boost is the opposite of a buck. What you need to do is just to rotate counterclockwise. So now you have same thing, letter T, right? And then start putting the component, right? So now the inductor is going to be at the front end, the switch going to be in the middle, right? Then we know the last one must be the diode. So diode is going to be on the output. That's your boost converter. Easy, isn't it? Just rotate your buck to counterclockwise. Did I say clockwise? Counterclockwise, and you get a boost, right? So right away, you know that boost is going to be good, bad, right? A buck is bad, good, right? This is good, this is bad, because we have a switch at the input, you have inductor at the output. A boost is the opposite, it's good, bad, right? You have inductor, and then you have a diode, which is also discontinuous in terms of current, right? So that's how I would memorize the difference between, not memorize the difference, but that's how I memorize how to draw a boost converter. It's just a buck rotated counterclockwise. Okay, all right. Here's our more complete circuit schematic of a buck. Still is power stage, right? And just like before, I put output capacitor, and there should be output. There should be input capacitor as well, but since we have an ideal source, I'm not going to draw that for you. But in real world, of course, you're going to have that input capacitor, right? Now, how many states do we have for a boost converter? The same as buck, only 2 states. Either the switch is on, the switch is off, right? Because that's the only switch that we have control of, right? Diode is not controllable, right? So the only switch that I can control is that one single switch right here, right? And what's nice about boost converter is that it's a low side switch. Remember the difference between high side and low side? This is a low side switch, meaning you can do an NFET, right? Because the source is at the stable node right there, which is ground, right? So if you use a MOSFET, this is going to be the gate, and that's going to be the source, right? And the source is at the ground connection, right? So that's convenient. You can use NFET, and NFET is more efficient than PFET. Right? Remember, in a buck converter, the switch is up here. So then you have to use PFET, or you can also use NFET, but then make sure that when you use NFET, the gate will always be higher than the source. And that's why if you buy some controllers for a buck, they're still using NFET because they use a bootstrap capacitor to make sure that the gate is always higher than the source, right? Imagine if the switch right here, right? The gate is actually connected to the switching node, and this node is not stable. This node is going up and down, positive, negative, positive, negative. So therefore, for a controller to be able to use NFET, it has to do extra. Right? Okay. All right. Then what else? I think I need to mention here. Okay, that's it for now. Now let's analyze this circuit. Right? I'm going to derive the transfer function. Right? Let me go back to here. You can see that it's not really that bad. Once you understand boost, I can go fast now. Okay. Again, buck boost. Buck boost converter. The first state is switch is on. Right? What happened when the switch is on? Well, here's what happened. Right? Here's on right there, and we have a diode here. Right? Like that. Like that. Okay. When the switch is on, what is the node here equal to? That's equal to ground, right? 0. Right? You're shorting this to ground. So you can see that anode is at 0 and cathode is at V out. So therefore, right away, diode is off. Agree? So now we have a switch on, diode is off. If that's the case, then what is VL equal to? Here's VL right there. What is VL on equal to? Easily we can see that VL on is equal to VS. What do I put here? VS or VN? I don't remember. VN. So VL on is equal to VN. Any question on that one? All right. So that's the first state. You can see that we are charging, right? We are charging this inductor. How do we know we are charging it? Well, because of LDIL dt, right? We know that VL on is equal to VL on is equal to LDIL dt. Right? So therefore, DIL on dt is equal to VL on L. Right? VL on is V in and divided by L. V in is positive, L is positive. So therefore, we have a positive slope. Is that a constant slope? Yes, it is, because V in is constant, L is constant, so positive constant. That proves to you that when switch is on, inductor current is charging with a linear slope. Good? All right. That's what happens with switch is on. What about when the switch is off? What happens there? When the switch is off, we have this circuit right here. Switch is off, right? Now during the transition, as soon as I turn the switch off, right, diode is still off, right? Remember, diode was off before, like this, right? So I just turned this switch off just now, right? I do have a control over this switch, but I don't have any control over that diode, right? So what's going to happen? What do you think is going to happen with that diode? As soon as I turn the switch off, of course, inductor will look for a path for it to discharge, right? Look, the inductor current doesn't have a path right now, right? So therefore, what's going to happen with the inductor? Now it's going to try to find a path, right? As soon as you turn off the switch, right, the inductor says, hey, you're cutting my my path. I need to find another path, right? In order to do that, the inductor will have to discharge. So now it's going to be minus plus, right? And here we have V out as well, right? And V out is also a positive voltage. This is also positive. So what do you think is going to happen? We have a diode that points that way, right? Points that way. What's going to happen with the anode right here? Well, of course, the inductor will keep fighting, right? Until this node is more positive than that node, right? So both of them are positive, but inductor will make sure that this will be always more than the cathode, right? Therefore, the inductor can discharge, right? Otherwise, you're going to see a spark across, this switch if it keeps opening like this, right? So the voltage keeps increasing until the anode, of course, quickly until the anode is more positive than the output voltage. If that's the case, then diode will turn on that way, right? And now you have another circuit where diode is on and switch is off. Any question on this? Now I'm going to put back the reference voltage. If you agree with that, what is the voltage across the inductor now when it's off? Voltage across the inductor is this node minus this node. right? What is that? Well, this node right there is equal to V out. That node right there is equal to V in. So I know this V in minus V out, or VL off. Okay. Now, why is that good to know? Because now, oh, before I go there, what about that inductor? Is that charging or discharging? Well, VL off is equal to L DIL of dt, right? And so therefore DIL of dt is equal to V in minus V out over L, right? Now we still don't know whether or not this is charging or discharging, right? Because I know that both of them are positive. V in is positive, V out is positive. So let's just wait until I derive the transfer function, right? And we go back to this point. So at this point, I know that VL on is equal to V in, and VL off is equal to, what is VL off equal to? V in minus V out. V in minus V out. I hate this mouse, okay, right there. Why is that important to know? Anybody? Why is it important to know VL on and VL off? Anybody? Just one person, come on. VL on is equal to V in.
It sets the discharging and charging state.
Yeah, but why do we need this equation for? To get what?
The current?
Duty cycle.
Duty cycle? No, the answer is to
current
know
waveform.
the transfer function of a boost converter. Remember, how do you derive a transfer function of a boost converter? Same as a buck converter. What is the equation that you need to apply? Remember the short way? How do you get V out over V in? How do you start? I ask you to memorize this. How do you start to find V out over V in? What will be the simplest way?
The duty cycle formula, the V out is equal to 1 minus dV in, or maybe a reverse.
How do you derive that? How do you derive that though?
I think you start with amp second.
Yes, you start from volt second balance. Please remember this, okay? Every one of you, please remember this. Very common interview question. They ask you to derive, right? They ask you to derive the transfer function. The easiest way is to apply VSB, volt second balance. How does it state? Can one of you tell me?
VL on times T on minus VL or plus VL off times T off.
Very good. Please remember this. Right, coming out of this class, I'm expecting you to know this. Right, somebody asks you to derive a buck boost, a boost. Start with volt second balance equation. VL on T on plus VL off T off. That's why I was trying to find this. I didn't want to tell you before that I'm trying to get volt second balance, but now you know why. I was trying to, I try to get VL on and VL off first. So now all that I need to do is to plug in VL on right there. That's V in. What is T on equal to? You know this? What is T on equal to?
DT.
DT plus VL off. Well, we have the VL off equation, V in minus V out. Well, what is T off equal to?
1 minus D times T.
Always, right? For a buck boost and buck boost is always the same. See that? That's all you need to derive the transfer function for a buck boost and buck boost. Start from volt second balance and know what VL on is and what VL off is. And the rest is going to be easy, right? T on is equal to DT, T off is equal to 1 minus DT, and the rest is just algebra, right? You cancel the T there, right? And you can start doing the algebra here. V in minus V out, V in times 1, V in V out, and then V in D, and then what else am I missing something here? V in times 1, and then V out, oh, okay, and then V in, and then plus V out D, there you go, sorry, there, right? And then you hopefully you'll see that some cancel, yeah, this one cancels, right? And now we have, if you rearrange the equation, you get V out equals to 1 over 1 minus D times V in. Right? That's it, right? That's all you need to do in order to derive the transfer function. What can you say about this transfer function? What can you say about the output voltage, knowing that 0 is less than D is less than 1? That the average output voltage is always higher than the input, right? Because D is, again, ranges from 0 to 1. Go ahead and plug that value here. Then you get output voltage that is always higher than input voltage. Therefore, this is called boost converter, right? Agree? Now, remember we were trying to get the slope right here, whether or not this is charging or discharging. I'm almost done. Now we know that V out is always larger than V in. So what do you think you get from V in minus V out? Is it positive or negative? Obviously, it's going to be negative, right? Because output voltage is always bigger than input voltage. And the denominator is positive. Negative divided by positive gives you negative, right? And it's also constant because V in is constant, V out is constant, L is constant. It's going to be a negative constant. So therefore, when the switch is off, the inductor current, just like a buck converter, will decrease, will discharge with a linear slope. So at the end, you're going to get triangular waveform as well. Linear slope when it's charging, and then another linear slope when it's discharging.